In this video, I will try to use my very advanced drawing software, aka Paint, to give you a basic understanding of what a derivative is, because that's a mathematical concept that we will be using in the next couple of videos. So if you are very familiar with the concept of derivative and if you know how to differentiate functions and etc., feel free to skip this video. But if you'd like to freshen up these concepts, feel free to stay. Also, if you've never heard of derivatives before, I would advise you, or I would recommend you, and this is from my personal perspective, I would recommend you to pause the video and go elsewhere to learn properly what derivatives are, because this will only be enough to get a very basic intuitive understanding. I will leave some useful links in the description for those of you who are more curious and like to get things straight in their heads. But for now, let me draw some function. So these are my axes, the x-axis and the y-axis. And now I'm going to draw a parabola, maybe something like this. Okay, and now let's pick a point, any point. It's not very relevant the point we choose, it's just we need a point in order to talk about derivatives. So let's say we pick this point right here, whose value of the function is right here. And now what we can ask is how much or how wildly is the function varying in this neighborhood. So when I look at points nearby, like this one or this one, how much does the function change from here to those places? Does it change a lot? Does it change just a little bit? For example, if we look at this point right here, now this is very imprecise, okay? So this is just us talking about derivatives. This is not mathematically precise. So from here to here, if I zoom in a little bit, okay, we can see the change in height. So the change in height was from more or less from here to here, right? Okay, so the line wasn't very good. Yeah, from here to here. So this was the change in height, this gap. For this change in, well, let's call it width. So I walked a little bit to the right and the function increased this bit. But if I were to pick a point, say around here, so if this was my starting point, now let me mark it. So if this was my starting point, then the value of the function, now I should decrease the zoom level, okay? So for this starting point, the function value would have been somewhere right here. And now, if I am to zoom in again, and I want the exact same step to the right. So from here to here, I walked a little bit to the right, and I want to reproduce this little jump. So let me go ahead and use my math editing skills to copy this. Why not? Maybe I didn't copy it correctly, sorry. So let me select this, let me copy and then paste. Okay, awesome. Now let's pretend this was over here. Okay. And now, so the jump is exactly the same because I copy pasted it. Now I just have to see where this goes. So let me draw the line. It's the correct width. Okay. And now let's see if I can do this correctly. Nope. Okay, perfect. Now of course it doesn't fit in the screen, so I have to do it again. Okay, I did it. Now it's very hard to see what the change in height was because these points, they have very similar heights, right? I guess you can see that. Can you? Okay. So the change was very little. Even though we walked the exact same bit, so let me decrease the zoom level again. So even though we walked the exact same bit to the right in these two locations, in one of them the change in height of the function was much bigger than the other. And derivatives are what quantify this change. So in here the change was more noticeable, and so for this, in this particular point over here, the derivative is going to be some number, some value. Let's pretend it was 2. And so because the change here was less noticeable, then that means the derivative here will be smaller. For example, it could have been 0.3, who knows. And then as you walk right, as we keep going, we'll reach a point in this function where the function is decreasing. So you can see here the function is no longer increasing, now it's decreasing. And in these cases, when the function decreases, then what we have is, I know the lines aren't aligned, but that's fine. Now the change in height is very noticeable again, but now instead of going up as we went right, we went down. So the value of the function decreased. And in here, the derivative is going to be a negative number. And notice that this gap is larger than this one, so it's going to be a negative number whose absolute value is larger than this one. So for example, -3. And what one does is, these steps we made over here to the right, these were drawn arbitrarily, right? I could have chosen them more to the right or more close together. And in fact, the derivative is what happens to this gap over here as this step size is made smaller and smaller. And in the limiting case, that is when we make this jump very, 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 very small, infinitely small, what we see is that these numbers right here, the derivatives of the function in those points, represent the slope of the lines that are tangent to this graph. So let's go through these terms step by step. So tangent means that it only touches exactly once. So this is not very good. Maybe something like this. Kind of. Okay. So this straight line is tangent to the graph because it only touches the graph here, more or less, because my drawings suck. So that's the tangent point. And then the slope is a measure of how slanted the line is. If the line is pointing up, then the slope is big, for example 5, and if the line is almost laying down, then the slope will be smaller, for example 0.5. This is the slope of the line. And turns out the slope matches these numbers right here. The slope is the derivative. It's defined as the derivative of the function in that point. And, well, why do we care? Because we will be drawing, well, not explicitly, but implicitly, this could be our loss function. And in here we can see in this region the loss is high, and in these regions the loss is low. And we will have our network, and then the output will be somewhere right here, for example. And let's say, okay, we want to make the loss smaller, so where do we want to go? Do we want to go right, or do we want to go left? Which one would you pick if you wanted to make this value smaller? Well, of course you could go very much to the right, but that's very far away. So we might as well just go to the left. And that's what we will be doing when we are training our network, is we will be inspecting these functions, finding their derivatives, and then using the derivatives to decide if we should go left or right. Because Notice when the numbers are positive, that means that going right goes up. And when the numbers are negative, going right goes down. And so because we want to decrease our loss function, we can see here we compute the derivative and it's a positive number. In this case, for example, 5, because the tangent line over here will be much more inclined than the one I drew before. So maybe this is the tangent line and it's going up much faster than this one over here. So the derivative has to be higher, the slope has to be higher. It could have been 5, who knows. And then 5 is a positive number, so that means that going right increases, but we don't want to increase the loss, we want to decrease it. So we have to go left. And then mathematics has all these fancy formulas to numerically, well, symbolically find the derivatives of the different functions. And those are rules that you can learn or that you can derive for yourself. And we will be using those, well, the most basic ones, we will be using those basic formulas to find the derivative of the loss function, so that given a network output, we can know whether we want to go left or right in order to tell our network what it should be aiming for.